So we're on day 2 of trig, and I want to just make sure that you check your unit circles with your degree and radian equivalents. You need to study those and look for patterns. You have to be able to convert back and forth pretty quickly. I suggest looking for patterns. So this is something that I would like you to do as a group. I would like you to go to your Google Hangout that I've sent to you. There's a 7th hour Google Hangout and there's a remote section Google Hangout. And I would like you to write down some patterns that you've seen to help you remember these. Because we're going to have some quick quizzes where I give you an angle and you have to write down its equivalent in degrees or radians. Okay, so just some patterns that I have seen, that any of those angles that are multiples of 45, they're always over 4. Any of those that are multiples of 30 or make 30-degree angles with the x-axis are over 6. And any angles that make 60 degrees with the x-axis are over 3. All right, something else that helps me, for example, if I were asking you to change 5 pi over 3 to degrees, we know that when we are changing to degrees, we take 180 over pi, okay? Well, you just basically know your pi's are going to reduce, so you don't need to think about that. And what I do is I just always take my denominator and take it into 18 because that's easy mental math. 3 goes into 18 6 times. 5 times 6 is 30, but it would have a 0 on it, so it's 300 degrees. So please share more patterns. I encourage you to make some flashcards to study these. Okay, so now let's go back to the notes that we began yesterday, and I'd like you to turn over and go to coterminal angles. Okay, some of the ideas and concepts that we are going to be talking about this week, you're not going to see how they all work together until the end of the week. Okay, so this idea of a coterminal angle, you will see how it is used. Right now, we just have to know how to calculate it and what its definition is. So a coterminal angle is an angle that shares the same initial side. Well, they all share the same initial side, but they share the same terminal side. So how can you find coterminal angles? Well, simply all you have to do is add or subtract multiples of 360, or if it's in radians, add or subtract multiples of 2 pi. Something else to always check your answers, graph to check, because when you go to graph the coterminal angles, they should end up in the same place of the unit circle. Okay, so let's take a look at example 7. I've asked you to find a positive and a negative coterminal angle with these. And every time I give you angles, I think a good habit is to think about where they are in which quadrant. Okay, so 50 degrees is in quadrant 1. So if I wanted to find a coterminal angle with this, I could add 360 or subtract 360. So if I add 360, I get 410 degrees, and think about why they're coterminal. If I go around one time, it's 360. 360 plus 50 is 410. All right, 50 minus 360. All right, so 50 minus 360 is negative 310. So negative 310. Wouldn't that mean I'd go around this way? So a negative 310. So if I go from here to here, that's a negative 270. 270 plus 40 more puts me at 50. All right, why don't you try, if you need to stop this, 7b with negative 258. Negative 258 would put me in quadrant 2. So if I add 360, I get 102, and if I subtract 360, I get negative 618. And as I've mentioned, always check by graphing. All right, if your angle is in radians, then you need to keep your coterminal angles in radians. All right, so negative 7 pi over 6. All right, where is that? Well, that would be in quadrant 2. Also, it is a good habit to think, okay, radians, what would that be in degrees? So again, studying those, eventually you should know negative 7 pi over 6 is negative 210. All right, but if you have to still do that in your head, take 6 into 18, that's 3. 3 times 7 is 21, put on a 0. All right, so anyway, that puts us in quadrant 2. So to find a coterminal angle, I can add 2 pi. So negative 7 pi over 6 plus 2 pi, or plus 12 pi over 6 to get a common denominator. That's 5 pi over 6. Okay, so 5 pi over 6. All right, so 5 pi over 6 is coterminal with negative 7 5 pi over 6. Let's see why. If 5 pi over 6 would be in quadrant 2, but also if I had to change that to degrees, would that be 150 degrees? All right, so if I graph 150, graph negative 210, yes, they end up in the same place. And then if I subtract 2 pi or negative 12 pi over 6, I get negative 19 pi over 6. All right, last one. So 5 pi over 4. All right, so first of all, you know, with denominators of over 4, those are multiples of 45. So you know it either has to be 135, or 45, 135, 225, or 315. All right, also, if something you put in your head, 4 goes into 180 45 times. This ends up being 225, which is quadrant 3. So anyway, if I add 2 pi, I get 13 pi over 4, and if I subtract 2 pi, I get negative 3 pi over 4. Also a good way to check, negative 3 pi over 4, that's a negative 135. So if I graphed 225 and graphed negative 135, they are at the same place. So coterminal angles share the same terminal side. So when a way to calculate those, add or subtract 360 or 2 pi. Now I want to go back to applications. And what is the big deal about radians? Okay, well, radians are a way to measure length. So as I mentioned in yesterday's video, that if I took a circle and wrapped a piece of yarn around it, all right, a circle would be the circumference around it, that's arc length. I can take that piece of yarn and actually measure it. So that is why when we're talking about anything with rotation, gears, pulleys, lots of engineering types of problems, that we deal with radians. Okay, so going on that same set of notes, let's take a look at applications. So as I mentioned, we've said this is a formula like distance equals rate times time. You need to know that arc length equals radius times theta. Okay, but theta is radians, radians. So in example 6, I said find the angle if the arc length is 3 meters and the radius is 1. All right, so if I put in 3 for S, 3 for S, 1 for R, I get 3 radians. And that's absolutely fine. Now, though, when I'm talking about an actual angle, sometimes it means more to us to change it to degrees. So where is 3 radians? All right, so you could change that to degrees if you wanted. But something else that I want you to do is, where is 3 radians? Do you know where that is? I think you have a good idea when I give you an angle in degrees that you know that 240 is in quadrant 3. But do you know where 3 radians is? So what I would like you to do is I want you to go to your unit circles, and I do want you to know those common angles in both degrees and radians, and those angles in radians in pi. But what I would like you to do is to take your calculator and actually convert those to decimals so that you have an idea of the real number that those radians are. Okay, so where would 3 radians be? Well, think about this. If I go over to 180 degrees, isn't that pi? And isn't pi approximately 3.14? So 3 radians would be in quadrant 2. Okay, so let's take a look at B. So if my arc length is 1.5, I don't remember the unit they gave, and my theta is pi over 4, find my radius. So all I do is take 1.5 divided by pi over 4, and I get 6 over pi, which is approximately 1.9099. Okay, so remember, theta is measured in radians. So when you use this, you have to make sure theta is in radians. All right, so now what I would like to do is I would like to go to another set of notes, and the front of the notes is about applications, talks about UPS and that, but I also want, and talks about linear velocity and angular velocity. Right now, we are just going to focus on theta equals r times theta, or arc length equals r times theta. So what I'd like you to do is go to the notes that look like this, but I want you to go to the other side where it talks about applications of radian measure. So if you need to stop this and get these out. Okay, so in example 4, poor Billy is being pulled up by a pulley. So it asked, what is theta if the radius of the pulley is 16 feet? So we're talking about something, a large contraption here. And we are raising Billy 5 feet. Okay, so what angle, so if say this was something being rescued or something, a large object being pulled up, what angle do we need to have this set? All right, so arc length equals r times theta. So my arc length is 5 feet. Why would that be? Well, think about if poor Billy, I didn't draw a stick figure here, but if poor Billy is hooked on here, all right, when we raise him up, isn't this going to wrap around the pulley? So you see how that would be arc length? The radius of this pulley is 16 feet. So 5 equals 16 theta, 5/16 equals theta. Now, that's fine. That's in radians, but for practical purposes, we should put this in degrees. So how am I going to put that in degrees? Well, I just took 5 divided by 16 and got 0.3125. Now, to change that to degrees, I multiply by 180 over pi, and we would get close to 18 degrees. Okay, let's take a look at B. So same situation. We have a radius of 16 feet, but now the angle has changed to 48.8 degrees, and we need to find the arc length. Okay, so if we had a situation and we needed to know how far this person would be pulled up, or whatever object's being pulled up, what would that be? That would be our arc length. Okay, so first of all, for practical purposes, when we're talking about angles, we typically say it in degrees. That's fine. But when we're using this, we have to convert it to radians. So when you use arc length equals r times theta, it has to be in radians. So my radius is 16 times my angle, but I put it in radians, and so that would end up being 13.63 feet. Okay, last one of these. We are now looking for the radius. Said the arc length was 10 feet and the angle was 42.5 degrees. So again, when we're talking about angles, the practical side of it is we use degrees. It's kind of like if you've taken physics, you talk about meters all the time. However, in America and the US, we use feet and inches. Okay, so we tend to talk about degrees, but if we're using this is about length, so that's why we always have to change our angle to radians. So I could have taken 42.5 and changed it to pi over 180 right away, and then taken that and taken 10 and divided by that, and I get about 13.48 feet. Okay, so now another application that I want you to go to is to find these notes. Right now, what I've done is all of these different applications I've given you, I'm trying to just pick out the ones that have arc length equals r times theta. So what I would like you to do is, let's take this out and we're going to do a couple of examples. What's kind of cool about this is another way to use arc length equals r times theta to actually find the distance between cities. As I mentioned in yesterday's video, one of the reasons we have trig is we know that the Earth is a sphere. So all of these grids, everything we use for GPS, all of these coordinates, we use the grids for our phones, etc., is based on a circular system. Okay, so if you want to take the time to read this, that we said Reno, Nevada is approximately due north of LA. So the latitude of Reno is 40 degrees north, while that of LA is 34 degrees north. So the north means the location is north of the equator. Now, for this to work though, these cities pretty much have to be north and south of each other. All right, so if the radius of the Earth, so if we were talking about kilometers, is 6,400 kilometers, find the north-south distance between the two cities. So we're using arc length equals r times theta. All right, so arc length equals r times theta. So I know that the radius of the Earth is 6,400 kilometers. Now, we have to take the distance between those, and the distance between those in degrees would be 40 minus 34, so that's 6. But we also have to change degrees to radians. So I'm going to multiply 6 by pi over 180, and if I take and multiply 6,400 times 6 times pi over 180, I get about 670 kilometers. Okay, so I should have held this up, and that was explaining it. All right, also kind of off the mark here, but there is a handout that I've attached here or will give to you, and it's a problem with a gears and a pulley, and it's a problem about the free throw line, which is kind of cool, or not free throw line, I'm sorry, it's the 3-point line. These are more examples of S equals R times theta, and I would like you to do those. Okay, so let's take a look here at number 1 at the bottom. All right, so Grand Portage, Minnesota is 44 degrees north, and New Orleans is 30 degrees north. Find the distance between the cities. Okay, so the radius of the Earth is 6,400 kilometers, but it is also 4,000 miles. And let's face it, in the U.S., we describe everything in miles. Okay, so arc length equals r times theta. So our radius is 4,000 miles. Now, the difference between the two cities is 14 degrees. But we have to change this to radians. So we take 14 times pi over 180, and Grand Portage, Minnesota and New Orleans are a little over 977 miles apart, which makes sense because if you think about Minnesota being in the north, New Orleans way down south, that distance seems logical. Okay, last one we're going to do, turn the page and go to number 3. This is asking what's the distance between New York, New York and Lima, Peru. All right, so New York, New York has a latitude reading of 41 degrees north, and Lima, Peru has a latitude reading of 12 degrees south. So what do you think we're going to do to find the distance or the angle between these two? Okay, we're not going to subtract because that's not the difference. This is north and this is south. We would have to add those two. Okay, so the arc length equals r times theta. My radius is 4,000 miles. The difference or the angle between those two is 53 degrees, but of course I change that to radians, and we get a little over 3,700 miles. Okay, so in summary, today we were talking about coterminal angles, which for right now you may not know their use, but coterminal angles, we add or subtract 360 or 2 pi. They should always end up in the same place when graphing. Secondly, the big application we talked about is arc length equals r times theta, where theta is always in radians.